research takes a long time. You look at some things that don't work out, you explore different areas, but it's a very rewarding process when you do get a great answer and can come up with a redesign or solve some problems with it.
Hi everyone, welcome to the Vandal Theory, a podcast about science and research at University of Idaho. I'm your host for the day, Danae Lenz. I am the External Communications Coordinator for U of I, and I am joined by Lee. Hi Lee.
Hey Danae. I'm Lee Cooper, science writer and editor here at University of Idaho. Happy to be here.
Today we're going to talk about solutions to some of life's mechanical problems. And I have a question to kick us off. Have you ever had a problem that you just lived with because you assumed it couldn't be fixed?
Yes. So I have very bad feet. My feet do not like their job description of walking. So me and shoes have a particularly contentious relationship. And I was about to do a 10-day walking extravaganza through England. And this feet thing's not new. I've had problems with my feet forever. And I had spent 6 months trying to find the right boots to bring. And after a couple days of walking around London, they were hurting. And I was like, this is just, is this just the way this is? This is done. And I was like, fine. I had an hour to kill before we had tickets to something. And I stopped into their running store in London, in downtown London. And I walked in and they measured me up and they're like, oh, well, I told them that, I'm usually an 8.5. And they're like, no, you're not. You're a 9. Absolutely. No questions asked. I'm like, are you sure? I'm not entirely sure that I trust this. I've been an 8.5 forever. And they're like, nope, I'm sorry, you're wrong. They were really no, it will be a fail if you walk out of the store with an 8 or an 8.5. And they felt like clown shoes. But I was so desperate for my feet to not be hurting that I bought them, and my feet haven't hurt since. All my shoes are worthless at this point because apparently I have the wrong size shoes. And I had been struggling with that for decades.
Sometimes you just need someone to come into a situation and be like, girl, no, you're wrong.
And you're wrong.
Yeah, I've also had some things like that happen in life, but more often it's not that I think it's unfixable. It's that I think it'll be a heavy lift or it'll cost me a lot of money or whatever. And so, especially I bought a house 8 years ago, and there were some things in this house that I just lived with for years. They were wrong, they were incorrect, and they were falling apart. And I was just like, it is what it is. And then one day I woke up and was like, I want to try to fix that thing. And it turns out it did not take all that much. All it took was just a little bit of curiosity to be like, what would it actually take to fix that thing?
A couple of YouTube watches. You're there.
Right. Yes, exactly. Sometimes not even that. Sometimes just using my brain power a little bit, So today we're going to talk to someone who has a lot of experience with this, and unlike us, he actually asks if they can be fixed. He and his students ask if these everyday problems can be fixed. His name is John Crepeau. He is a mechanical engineering professor at U of I, and he has had a hand in making all sorts of things, from a nuclear-powered Mars hopper to reimagining medical equipment. And today we're going to talk about his experiments and also the role that he's been playing in the future of sustainable jet fuel. Ready to get into it?
Fueled up and ready to go.
Hi, John. Welcome to the podcast.
Danae, thank you very much for this opportunity to talk about some of the stuff that I've done here at the University of Idaho. I appreciate the invitation.
Yeah, absolutely. To start us off, can you just give us a quick bio about yourself? Let us know about who you are and what you do.
Sure. My name is John Crepeau. I am a professor of mechanical engineering here at the University of Idaho. I am currently in my 31st year here with the U of I. So this has obviously been my career position. I grew up in Southern California, San Diego. I got my bachelor's degree at the University of California at Berkeley. It was a great experience. I really loved it. In fact, being at Berkeley, that really was the driver for my decision to be in academia. I loved it so much. I said, I want to spend my career at a university. After I graduated, I worked for a year at a company in Southern California, Litton Guidance and Control. We built ring laser gyroscopes. Then after that, I took a little hiatus. I served as a church missionary in Guatemala for 2 years. Then I went on to graduate school, University of Utah. Got my master's and PhD degrees there, had a great experience, graduated in 1991. After that, I worked for some companies in the Salt Lake area, and then I received a fellowship from the National Science Foundation to do some research in Berlin, Germany. What a great experience. We lived there for a year. I did some work in fluid mechanics. We actually lived in the former East Berlin, and this was just a couple of years after the fall of the Berlin Wall. So there were still lots of remnants of the old East Germany that were there. After that was completed, then I got a job at the University of Idaho at our extension campus in Idaho Falls, which was just a great experience as well. We lived for 15 years in Idaho Falls. The position there, one of our responsibilities is to help with the Idaho National Laboratory. That was really the initiation of my research work in what's called the Stefan problem, or phase change. So it's when materials can melt because of chemical reactions going on within, not necessarily chemical reactions, because of heat generated within the material itself. So as a great example of that is a nuclear fuel rod meltdown. The nuclear reaction kind of goes crazy. It starts to heat from the inside and can actually melt the material from the inside out. So we just did some mathematical modeling for that. We were there for 15 years. And then in 2009, we came up to Moscow and I became the mechanical engineering department chair.
So I know over the course of your career, you've had your hands in a lot of different kinds of things. Can you just give us a few examples of some of those things? I know you've done some cool work.
Sure. I'd be happy to. One of the reasons that I took a job at a university, and here at the University of Idaho, is that a position like this really allows you to explore and do work in areas that are of interest to you. One of the projects that we worked on, and this is something that began in Idaho Falls, is to work on what's called the Mars Hopper project. So there are some exploration vehicles that are currently on Mars. They use solar power to move from one location to the other. The solar energy then charges an electrical system, and they're different types of rovers, but essentially you can move like a little car, a little vehicle from one location to the other. Some downsides to that is they move very slowly. Okay, they can't go a long distance. And at a Martian nighttime, if there's no sun, there's no way to generate electricity. So with this Mars Hopper project, what we did is use what's called a radioisotope thermoelectric generator. It's essentially a little nuclear power plant, has a little nuclear fuel on the inside, and that generates heat, which in turn can generate electricity. And so the idea behind the Mars Hopper is to suck in Martian atmospheric gas, which is primarily carbon dioxide, compress it in a tank, and then once it gets compressed, you open a valve, and that high pressure gas goes through a little rocket nozzle, and that Mars Hopper, then that whole vehicle can jump from one location to another. So it's about a 2 to 3 kilometer jump from one place to the other. It's kind of neat. So it functions at nighttime because it doesn't need solar energy. It's not a chemical rocket. When a chemical rocket burns, all those chemicals are gone. This just uses the constant property of compressing a little tank of gas and use that to thrust your vehicle from one location to the other.
It's crazy how far it jumps, though. Like, when you were describing this, I was thinking it would be hopping, 10 feet. Like, how big is this thing?
Okay, so it would be roughly about a meter cubed. There's some issues with that. I mean, obviously, as this thing hops and lands, it's kind of a crash landing. So you have to make sure that it lands properly. It has to land in a vertical orientation. So we did some structural work to mitigate some of those crashing problems and kind of have shock absorbers and so on. The interesting part about this, and maybe to answer your question, is that the gravitational force on Mars is much less than it is here on Earth. So you could provide the same amount of thrust on Mars that you would have on Earth, but since the gravity pull is lower, you can actually hop farther distances. So sadly, we've tried to sell that to NASA, and we didn't get very far. But nevertheless, it provided some great student design projects that they were able to work on that project, and that was a lot of fun.
I know you have some other things that you've worked on with students that have ended up being kind of cool, right?
Yeah. As I mentioned, one of the great things about a position like this is that you can pursue research areas that aren't necessarily in your main field. And so I actually have done some work with medical devices, doing some redesign of medical devices. Our son was a student here in the WAMI program, the medical education program, and we were talking over lunch one day, and he was talking about catheters. And when a catheter is inside a human body for an extended period of time, you can get a lot of bacteria formation on the outside of that catheter, and people can get urinary tract infections because of that. And so I just thought, as an engineer, I never really thought of that problem, but we had a student design team that redesigned the outer portion of that catheter so that you could actually flush some fluid, not through the catheter, but on the outside of the catheter between the catheter wall and the urethra wall to kind of clean out any of the bacteria that would accumulate there. And so it would minimize the number of urinary tract infections that occur. So that was kind of a fun project. And our student design team, actually, we worked with our College of Business and went to some pitch competitions, and they won $16,000 at 3 different pitch competitions. That's pretty awesome for a student, get a few $1,000s of walking around money to help you out. And they did a great job on that. We worked on another project with the WAMI program. So we have close ties with our medical program here. And they admitted a student a few years ago that was a tetraplegic. Someone that is a tetraplegic is in a wheelchair and has limited use of their arms. And so they're in a wheelchair and move around and do stuff. And I just thought, well, that's pretty cool that you would admit a student that is a tetraplegic. How would you do an operation or work in the emergency room or something like that? And it turns out that there are other areas of medicine that she could do her work. Anyhow, as part of the medical education program, you have to be able to perform CPR. And so the WAMI school director came to us and said, hey, what could you do some of your students do to come up with some design to help this student in a wheelchair be able to do CPR? So our students thought about it for a while, and we worked with them, and they came up with this little device, kind of a cage, where all she would have to do is sit in her wheelchair, get connected to this cage, which is something that she could do. And then wherever the little resuscitation mannequin is, she could drive her little device close to it. And then all she essentially needed to do was sit in her chair and extend her arms, kind of like doing a vertical push-up, so to speak. And that would push this cage, and it had a little lever on the bottom, and that would apply a compression to the mannequin's chest. So these students came up with a design to help this medical student who is a tetraplegic to be able to get her medical degree. And that, for me, is one of the most exciting, fulfilling, wonderful things that we had our students do to work on that.
I consider myself to be a curious person, but especially the catheter thing, I just think of that as it is what it is. It would never occur to me. Well, and I don't have the skills either to actually change it, but you and your students do. But it would never occur to me that it could be better,
Yeah.
And so I love that you guys are out there thinking these big thoughts and making things better.
So it's kind of interesting when a patient goes to the hospital, has a catheter inserted, and gets a urinary tract infection because of that while they're at the hospital. Insurance will not cover that because the insurance considers the hospital as the cause of that infection. So there is an enormous incentive to reduce. I mean, naturally, we would want to reduce infections anyway, because that's the right thing to do. But hospitals want to reduce their costs and insurance costs. And so here's another way of doing that. And just this current academic year, we have a group of students that are working on what's called a speculum. Most women are aware of that. That is done in pelvic examinations, and that is a very uncomfortable kind of process. I can't speak from experience, but as I've been visiting with my wife and other females can acknowledge that. So they are working to redesign a device to make that process a little bit more comfortable as well. It's just so exciting to be able to use our engineering skills to go and help people. What a great use of the training that we have.
Yeah, I totally agree. That's great.
Let me just say one other thing, an interesting project that I've worked on. I mentioned we did some mathematical modeling for the Idaho National Laboratory, and that particular problem in the field is called the Stefan problem. I'm kind of a history buff. I enjoy that very much. And so normally when I give a presentation, I always like to take a minute or two to say, okay, we're working on the Stefan problem. Who was Stefan? And then give a little blurb about that person. So anyway, as I started to look into getting this presentation together to talk about Joseph Stefan, I came to realize that he really had his fingers in a number of different fields within physics and in engineering. And it turned out that Stefan is kind of an anonymous figure. He lived in Vienna, was a professor at the University of Vienna, and that he did a lot of work and didn't get a lot of credit. He's not a super well-known scientist. And so I'm always a fan of building up people that have done a lot of great work, but are kind of anonymous. And so I actually edited a book. We had some articles submitted or contributed, from other researchers in the field that touched on various problems that Stefan worked on. So that was kind of a fun thing. And again, that's a great thing about working at a university like this, is that you can do, for me, a medical engineer that did work in fluid mechanics, I could do heat transfer work, I could do Mars exploration rovers, I could work in medical devices, I could do in history if I wanted to. So that's been a real exciting thing.
I know that you recently got a Fulbright fellowship. What are you going to be doing? How did that come about? Yeah.
I have been interested in doing like some of the Mars exploration work. Another project that I worked on with my students was to come up with a launch vehicle. It's called an integrated rocket ramjet. So it had a combined solid rocket motor with a ramjet engine in it, all combined in one single device. So I'm interested in space and high-speed flows and things like that. We were interested in doing some research abroad, applying for a Fulbright fellowship, and I found an institution in the city of Graz, that's G-R-A-Z, in Austria. Interestingly enough, that's where Arnold Schwarzenegger's from. Not that that has anything to do with the project here, but at the University of Applied Sciences, and in German, it's the FH Joanneum University, they have an institute for aviation. And so I thought, that'd be kind of cool. I could apply some of my engineering knowledge in both heat transfer, thermodynamics, and fluid mechanics to some problems that they might be interested in. Well, it turns out that this Institute of Aviation in Graz had been doing some work in using hydrogen as a fuel in aviation engines. So hydrogen is a very energetic material. Sometimes it can be explosively energetic, which is a bad thing. It has a very low density, which means that you need to have a large volume to store significant amounts of it. It's not a real super dense fuel, but it provides a lot of energy from it. They had talked about maybe taking that hydrogen, and instead of making it into a gaseous compressed gas or liquid, they actually wanted to freeze it, use cryogenic hydrogen, freeze it, and then somehow expand that, have the gas sublimate, and then use the gas that comes out of that solid material to use as an aviation fuel. And I just thought, okay, I could probably help out with that. I had a student by the name of Jake Leachman. He is now a professor at Washington State University, so just a few miles away here. And he is one of the world's leader in using hydrogen as a fuel. He's got a wonderful, wonderful laboratory in Pullman. He really has the ear of a lot of companies that are interested in sustainable fuels that don't pollute. When hydrogen reacts with oxygen, it produces water, So that's kind of a cool thing. So I went and I bent his ear and we talked a little bit about some of the projects we could work on. And so I talked to this professor in Graz, Austria, explained some of the expertise that I had. And he said, I think that you could contribute to the work that we have here. So I wrote up a little application to see what we could do to kind of optimize the process of going from solid hydrogen to liquid hydrogen to then gaseous hydrogen, which could finally be used as a combustion material to use as fuel in an airplane. So I'm going to be going over there to help optimize that process, make it more efficient. There's a thermodynamics analysis technique called exergy optimization. So we'll use some of that exergy analysis to see if we can optimize that process of taking that solid hydrogen and turning it into gaseous hydrogen so that you can have an airplane that is powered with hydrogen.
And are you optimistic that this is going to work, that you're going to be able to figure it out?
I would say yes, with some constraints. So my Fulbright, we will be there for a little over 4 months, about 5 months. Can we solve the world's problem in getting combustion out of that in 4 months? Clearly not. Clearly not. However, we can establish a very strong foundation and a strong network between my work with them, connect them with the folks at Washington State University with the hydrogen research that they do there. And so that we could really start a foundation, get really a map forward on how we could progress. And then once we kind of get those details out, then we can go get additional funding. The aviation industry in Europe is very interested in using hydrogen fuels. And I know that here in the United States, there are many companies that are looking to use hydrogen for aviation fuels as well. It would be a great start, is a short answer to your question there.
Okay. Yeah, and I guess you sort of answered my question of the broader implications of it. It's clear that this is a product that people want, which is pretty cool.
So industry is excited to have it. Research, I will be very honest with you, research takes a long time. You look at some things that don't work out, you explore different areas, but it's a very rewarding process when you do get a great answer and can come up with a redesign or solve some problems with it.
Awesome. We'll have to touch bases when you get back because I'm curious to see what you find out.
I would love to.
All right. That was, I think, everything we wanted to touch on today, but I just wanted to ask you, what do you want people to take away from this conversation about your research? Literally anything.
Sure. Universities are a great place to do basic research and to solve problems that affect people. For me, it has been a privilege to work on all the projects that I've worked on, as fun as they are, but to work on medical devices that can help save lives, that help people get through college is a very rewarding thing. To be able to work with students that I love. I mean, I love to teach classes. I love to do research, and to see them progress and get that work done is awesome. Again, very rewarding, and just makes a career at a university that's special. And the opportunities then to do this work in aviation fuels, to make them more sustainable, to make them less polluting and cleaner. Again, we can use our engineering skills and talents to help the world be a better place. And that's something that I'm privileged to be a part of, and I'm very grateful for that.
Thank you so much for being on the podcast. This has been a great conversation.
You are very welcome. I have enjoyed it as well. And I look forward to visiting with you again next year sometime, whenever I can fit in the schedule.
Okay, so what did you think about the conversation?
Oh, that was interesting. I think the biggest thing for me is I kept thinking about it from a student's perspective, and the fact that engineering was never my cup of tea or anything, but if that had been what really excited me and interested me, in college, being able to walk in the front door and have a professor say, all right, come on over. Today you're going to work on, a Mars hopper or this thing that could save lives in hospitals. And actually be able to do that, that's how you get people to love their careers. That's how you fall in love with what you're doing. He provides such a wonderful opportunity for our students. Just really inspiring.
No, I definitely agree. I think he clearly fosters this sense of curiosity in his students, and that's a problem. Go fix that thing. That sounds great. I just think it's so cool that higher ed can really just enhance people's curiosity and foster it. And for both his students and for him, he said that working in higher ed, that if he has a question, he's encouraged to go seek out the answer to that. And I think that's how lots of great things happen in life, is just people asking questions and having the resources to answer them.
I agree. Absolutely. It's so nice to be able to actually have the opportunities to chase the rabbit down the rabbit hole and check out, see where something leads.
Thank you for listening to the Vandal Theory. You can visit our website at uidaho.edu for more about our research. Email us at vandaltheory@uidaho.edu. We are on all of the podcasting platforms, so please rate and review and subscribe. I'm Danae Lenz.
And I'm Lee Cooper.
Thanks for joining us.